So I'm going to be talking about writing Go analyses and a little bit about using them. So this is going to be fun. So first, let me talk about myself. I am Michael Matloob, and I work on the Go team at Google, and I focus on developer tools like analysis. And especially, I work on the golang.org/x/tools/go/analysis package. Here's the Go doc. So the analysis package provides a framework for writing analyzers for Go. Okay, and what are these analyses? So analyses are programs that can look at programs, examine them, and provide you information about them. It could say, oh, this is a bug. Your style isn't great. Anything that a computer can look at your program and tell you how to improve it or give you suggestions or feedback or whatever. So let's look at an example of what an analyzer can do for you. Here's a package that you might be using in your code. This is the comp package. It's really useful for comparing two values for equality, for example, in tests, provides a bunch of goodies that reflect deep equal doesn't, so I recommend you use this in your tests instead. Cool, so we have this package. It compares, equal compares x and y for equality, and x and y have to be the same type. Cool. Okay, so here's what we're going to be comparing. Pretty straightforward. We have a type x. It doesn't have any fields. All x's are the same. Great for comparing. It's going to be easy. We have a string method. It's just going to print instance of x because they don't have any fields and they're all the same. And new x will return a new x. Now we're going to write a test. So we have our want and our got as we do in Go. And we are going to use comp equal to compare them for equality, and if they're not equal, which, why would that happen? We're going to return an error. So far, so good, right? No. So we get an error, and this error kind of sucks. It says that we got an instance of an x, and we want an instance of an x, and they look the same, and now we're stuck. And we spend tens of minutes trying to debug this. What's the problem? Yes. The problem is that got is a pointer to x and want is an x. And it's hard to see this looking at the test sometimes. You can just stare at it and like, got and want look the same. All x's are the same. But, you know, this is just something that is easy for a computer to look at and hard for a person to look at. And computer knows this rule, that all arguments to comp equal should have the same type. So what do? I think I'm spoiling the solution a little bit. We're going to write another program that's going to check our program, and it's going to find errors for us. And this program could tell us, oh, you should be calling comp equals with two arguments of the same type. Let me demonstrate. So I'm going to go to my terminal. So I am going, oh, this is kind of annoying. Okay, so I'm just going to, sorry. This is kind of hard turning my head around. Okay. Okay, so this code is what I showed you before. I just want to give you evidence that there's nothing strange going on. Okay, so now I'm going to check this code using a program that I cooked in my TV show oven. And it's going to check it and find our errors for us. And I need to provide relative path because I'm in a module. Oh, wow. So it says comp equals arguments must have the same type, but it's called with a pointer to x and an x. So this is exactly what we needed when we were trying to figure out what was going on. So for this, we needed to know to run this tool to see this message. So it might not seem that helpful, but I'll show you a case where it's like even more helpful later on. Okay, so amazing, no? So that was an analyzer. The analyzer examined our code, provided diagnostics. That was a message that it printed out. In this case, the diagnostic was an error with our program, but again, the diagnostic can be anything. It could be formatting, it could be suggestions for how to improve your code, anything that a computer can look at and provide feedback for. And it's helpful for spotting errors that humans can miss. So this is what I'm pitching as like the main use for analyses. Like, write a program that can do what computers do best and find things that they know are always errors and show them to humans who are dumb and can't find them easily. Okay, so that's the concept of an analyzer. Let me show you 2 examples of analyzers in the wild. So here's GoVet. You've probably used GoVet. It ships with Go. It runs when some of the vet analyses run when you run Go test, and it can help you find various issues with your code that the compiler will let through, but GoVet knows is always wrong with your code. There's also static check. It provides a set of analyses that can find a whole wide variety of issues with your programs that you can fix, that are almost always problems with your code. And both vet and static check are sets of analyses that are written using the analysis framework that I'm going to show you. So there's a whole lot of examples that you can look at for analyses written using the analysis framework. So let's look at one of those, which is the example in this presentation. So I'm going to show you how you can write an analysis to check arguments to comp equal. Code, yum. Okay, so we're going to start every analysis with this analyzer value. So this provides a configuration for writing an analysis, and that the framework can use to run the analysis. So every analyzer has a name. We're just going to call this comp equal because it's checking calls to comp.equal. And the doc is going to say exactly that. That's useful when someone is trying to figure out what the analyzer is doing. Then there's a requires. So requires allows you to say that your analysis depends on the result of another analysis. And I'll go a little bit into what the analysis we're depending on does later. Finally, there is a run function. So this actually does the work of analyzing your code. It takes the syntax and the types of your code, and it produces diagnostics like that message that we saw printed out to the terminal that tell users what's wrong, what they can fix with their code. Oh, syntax and types. So what are syntax and types? Let me show you with a diagram. So we have this code, comp equal, got want. That's just a string. And the syntax is a structural representation. So now all these yellow bubbles are structs that we can look at and examine and then try to figure out what's going on so we don't have to parse the code ourselves. The types are annotations on the syntax. We have code called a type checker, and what that does is it examines the syntax and it says, oh, this function call, which corresponds to all of comp equal got want, evaluates the Boolean, because that's a return type of a function. And we know that comp equal is a function, so it has a function type. And we know that got is a pointer to x and want is an x, because the type checker examined the code and knows that that's what the types of those variables are. And this is really useful for us in writing our analyzer. All we need to do is see, when we're looking at a function call, are we calling comp equal? If we are, is the type that the type checker figured out for got different than the type that it figured out for want. And if that's the case, then we can report a diagnostic to the user. So this type data is very useful for us when we're writing an analysis, and I'll show you how we use it. Okay, so we're writing our run function. Run takes as input an analyzer.pass. So analyzer.pass is our main touch point when we're working with the analysis package. So it provides both our input, which is the syntax and the types, and our output, which is the diagnostics. So it's kind of what we do, where we do everything with the analysis package. Then the analysis, each analyzer can return a value that's used by other analyzers that depend on it. In this case, our analyzer is not returning values to be used by other analyzers. It just returns diagnostics that are looked at by users. So we're just going to return nil. But we do depend on the result of another analyzer, which is the inspect analysis. And what inspect does is it provides a summary of the code that it's looking at, which makes it easy for us to examine it. So what we're going to do is we're going to use result of, which maps the dependent analyzer types to the results that they have, and we know that it returns an inspector, so we could just do a type assertion right off the bat. And it provides to us a useful function. This preorder function will allow us to iterate through the syntax and only look at function calls. We're going to filter to only look at call expressions, which are the syntax type, struct type, for function calls. And for all of those, we're going to call inspect node. And inspect node will get all those call expressions and actually do the work of determining whether it's a call to comp equal where the argument types don't match and reporting a diagnostic. So all the main work is going to be done in there. So let's look at the implementation of inspect node. We have 3 steps. The first step is that we're going to extract the function information. The second step is we're going to check to see if the function that we're calling is comp equal. And then we're going to see if the argument types aren't the same. And if they aren't the same, then we're going to report a diagnostic to the user. So these are the 3 steps we're going to follow. Let's start with step 1. So because we called preorder with a filter for call expressions, we know that we're only looking at call expressions right now. We can do a type assertion right off the bat. Then we use typeutil.callee, and what this does is it grabs type information about the function that we're calling, and then we can check to see if we're calling the right function. And now we're going to do a type assertion to functions. So not everything that looks like a function in Go, function call in Go, is actually a function. Like there are other things, you have parentheses, they look like function calls, but they aren't. So in some cases, we're going to get nil, and we'll just return, we don't really care about those. Okay, so now we have a function call, and we have the information about the function that we're calling. Let's check to see if it's the right function. And we're going to do that by checking the name of the function. This is package path modified. So if it's the right package path and the right function name, then we're calling comp equal. And if we're not, then we don't care about this function call. There's nothing we can report diagnostic wise about this function, so we're just going to return early. And now we know that we're calling comp equals, so all we have to do is check to see that the types match. And if they don't, we can report a diagnostic. So let's grab the arguments off of the function call, and then we're going to get the type information. So the pass contains the type information in this typesinfo.typesMap. And what this does is this allows us to get from the syntax to the types. Let's go back to this diagram, right? So the syntax were these yellow bubbles, which corresponded to the actual structure of the parsed program, while the types were the information that the compiler or that the type checker determined each expression to evaluate to. And this types info allows us to jump from the syntax to the types. So that's what we're doing here. Now we know the types of the two arguments. And all we have to do is check to see if the types are the same. And if they aren't the same, we're going to report to the user that there's something wrong. We'll tell them where that wrong thing is, pauses the location of the function call in the code, and we're going to give this message, which is printed out in the diagnostic. And we were in analysis. So let's look at the steps that we took to write this analysis. First, we filter the nodes that we care about. We care about function calls, and the rest of them we don't even look at. Then we examine the syntax and the type information to meet a condition. We care about function calls to comp equals, where the types of the arguments are not the same. And if that condition is met, we report a diagnostic. So we're in analysis. But can we make it even better? I think we can. And we can use two features of the analysis framework to make things even better and report more information in our analyzer. And that's facts and fixes. So let's talk about facts first. Facts allow us to create annotations. So the same way we were able to get from the syntax the type information, we can create additional annotations that we can attach to our code that we can look at when we're doing our analysis. So let me show you an example of how facts could be useful. So what we might want to do is generalize our analysis to learn which functions require the same argument types. We hard-coded the name of comp equal in our analyzer, but we might want to become more general than that. And then we can report the bad usages of those functions the same way we did with comp equal. So let me show you how this might work. I'll define this annotate package that has the same type function in it. And then when I call same type in another function, I'll consider that a communication to the analysis framework that it should check that whenever that function is called, it's called with the same types. So we're creating an annotation by putting this call to same type in equal. Then when I call this function, test something with myComp.equals with A and B, whose types are not the same, it will produce this diagnostic, the same way that it did earlier when we were calling the real comp.equal. So that's what we're going to use facts for. So how can we use facts for this? What we're going to do is we're going to attach a fact to the definition of the function when we see that it calls the annotation function. And then later, when we see usages of that function, we're going to check to see if that fact was there, if it had been attached earlier, and if it had, then we know to check that the arguments have the same type. So here is what a function definition might look like syntax-wise. It has the name of the function, has a signature, has the body, and the body in turn contains this call to same type and has a bunch of other stuff that we're just going to ignore. And when we see that we're looking at the definition of a function that contains a call to same type, we put this little tag on it. We're going to say, this is a function that has the same type annotation on it, and this is what a fact is. It's a tag that we can attach to parts of our code. And this tag is going to be visible to us later when we're checking the call to myComp.equals. So instead of checking the name, which was hard-coded before, we will check to see if this fact, this tag, is present. And if it is, then we know that we can check, or that we should check, the arguments to see that they have the same type. So that's facts. This is just a light overview, but there's a lot more in the documentation in the modular analysis with facts section of the Go Analysis Go doc. So that's facts. Now suggested fixes. Suggested fixes let your analysis suggest replacement code for bad code, and this replacement can be accepted directly in your editor. Demo time. Okay, so I've got the code that we were looking at earlier open in VS Code, and this is way too big. So this is the same as what we were looking at earlier. And I'm going to show you something else before I show you suggested fixes. So this is where analyses become really useful. So we don't need to know to run this check program because our editor can run our analyses for us and then provide these squiggly lines when there's something wrong with it. So right now, we can see that there's something wrong with the call to comp equals as we're writing it. And we can fix it before we even run the failing test. Okay. Now the next thing I'm going to show you is the suggested fix. So this quick fix button is showing up because this analysis has a suggested fix associated with it. And what this fix is going to do is it's going to fix this type difference here because got is a pointer to x and want is an x by just dereferencing got and just sticking a star in front of it. So no star right now. And I'm going to click this it says dereference pointer here, and boom, there's a star. And now I fixed this issue. Yes, thank you. Remember to applaud like that every time you fix a suggested fix in your editor. Okay, suggested fixes. We've seen how it works. Let's see how we can implement it. Okay, this was step 3 of our analysis. This is where we checked to see that the types were the same. And we're going to change the code that reported a diagnostic to also add a suggested fix. So this is going to look like this. And the first step to check to see the types are the same is the same as before. If they're not the same, we're going to go through the work of preparing a diagnostic for the user. But this time, we're going to have a list of suggested fixes that we can show to the user. Now, we can't suggest fixes for everything here. The 2 types that they could be calling comp equals with could be completely unrelated. The code could be total gibberish. But we're going to suggest fixes for a case where we know that there could be something we could do. So if one of the types is a pointer to the other one, we could try dereferencing that first type, and then the 2 types will be the same. So that's all we're going to try to fix. So we're going to have this isPointer2 function, and if the first type is a pointer to the second type, we're going to generate a suggested fix that dereferences that pointer, and we're just going to add it to our bag of fixes. And same vice versa, if the second type is a pointer to the first type, we're going to generate a suggested fix. And then we're going to report this diagnostic with the suggested fix to the user, and we're passing in the fixes, and then that's going to get threaded through the analysis framework. Okay, so this introduced 3 functions: isPointer2, fix dereference, and report with fixesf. So let's look at the implementations for each of those in turn, starting with isPointer2. So what this is going to do is first let's see if the first type is even a pointer. And if the first type is a pointer type, if this type assertion succeeds, then what we're going to do is we're going to check the lem. So the lem of a pointer type is the type that it's pointing to. And we're going to check to see if that's the same as the second type. And if it is, if they're the same, then we know that the first type is a pointer to the second type. So that's isPointer2. Great. Now fix dereference. This is going to generate our suggested fixes by dereferencing the value. So what we need to do to prepare a suggested fix is to get the text of the code that we want to replace the bad code with. So we're just going to have this buffer that we're going to prepare our code into. And we're going to call format.node that essentially gofumps syntax into a buffer. And the syntax that we're going to put into that buffer is a star expr of the code that we want to dereference. So star expr is just what it sounds like. It's an expression that adds a little star in front of some other one. And so this is going to do all the work of adding like the right parentheses everywhere and all that. It's going to be great. And it just puts a little star in front of whatever we're dereferencing. And that's that. Okay, so now we have the code that we want to replace the other code with. We just have to generate a suggested fix. And the suggested fix has a message. So this is what appeared in the quick fixes dialog as the option for us when we were suggesting a fix. It just says dereference pointer. It could say anything. And now we have the text edits, which is the actual code replacement in our suggested fix. And we're saying replace the code that has the position of expr. So pause is the start position and end is the end position. And we're going to replace that range with the new code. And finally, we return this back to the caller. So that's fix dereference, which generates the suggested fix. Finally, report with fixes_f. This is just a wrapper around the raw diagnostic reporting code. So what this is going to do is call pass report with this raw diagnostic. It has a start and end position. And this is what specifies the range that we got those yellow squigglies for in VS Code. We have a message. This is the same as before. And now we have the suggested fixes, which appear on the diagnostic. And then this gets threaded through to the user or to the editor or whatever. OK, that's all the code we're going to see. We have our analysis. What can we do with it now that we've written this configuration, the code that actually does the analysis? The first thing we could do is we can write a command line tool. And the command line tool is the same as the check tool that we saw before. And let's see the code for that. So the analysis framework provides this single checker package. Single checker provides a main, which will do all the work of reading your code, type checking it, analyzing it, and then running your analysis on that code, and then showing the diagnostic to the user in their terminal. And all we have to do to run this is to provide that analyzer value that we defined before. And this creates the main for that check program that I showed you earlier. That's it. The next thing you could do is to contribute to xtools and GoPlease. We would love to get more analyses that we can run in users' editors. So what is GoPlease? GoPlease is the Go language server protocol server. So this is a server that runs on your workstation behind your editor. And your editor asks it for all the language smartness that it needs. So jumping to definition or autocomplete, or most usefully to us, running analyses. So when we looked at our code in VS Code, it was talking to GoPlease, which ran our analysis and then provided the diagnostic back to the editor. And you can add new analyses to GoPlease that can run in users' editors and find more bugs for them. So this is kind of what it looks like. This is real code in GoPlease, and we just stick our comp equal analyzer into it, and that's it. Then it'll run the analyzer for the user. And the final thing you could do is you could write a library-specific analyzer. So the example in this presentation was we wrote an analysis that checked for correct usage of comp equal. You could be writing a library that you want to make sure users are holding correctly. So to do that, you can write an analyzer that you can distribute with your library, and people can run it on their code to make sure that they're using it correctly. So this is a great way to find bugs with the usage of your libraries. So that's that. I think that writing analyzers is a superpower, and I hope you use your powers to prevent bugs. Thank you. Okay, you're talking about the fact example, right? So, oh yes, yes. So the question was, why did we use a function call that was adding code to prepare an annotation in our facts example instead of using a comment, right? So this was just to make it easy to prepare our example. Um, I don't really like the comment annotations. I don't think there are any really great ways of doing annotations. That's kind of an unsolved problem. That was just one option for something you could do, just to demonstrate how facts work. Any other questions? Oh, great question. How do I test my analyzer? So we have this great testing framework for analyzers. Basically, I think I could show this to you. So, where is this? Oh, it's not here. So I kind of want. So basically, we have this framework that will run your analyzers, and then you have comments in the code that in like the test code that it's running your analyzer on that says want, and then like the text of the diagnostic, and it'll just check to see that the diagnostics match what your test files say. It's really easy to use. I really like the way you can test analyzers. It's a blast. Um, so the API that the text editor uses is the language server protocol API. So you can go just search for language server protocol. It's like the standard API that's defined by like it was originally created by Microsoft, but it's used by a number of people. And so we made our own language server protocol service called GoPlease that communicates this protocol, and a number of editors use it, and it supports analyses, but it supports all the other stuff that like editors want. Um, so the question was if there's a way for library owners to publish and advertise the analyses for the library. There's no like standard way of doing it yet. My suggestion is for now, just like publish the single checker or multi-checker that runs your analyzers with your library, and put in your README, like you can run this to check it. I think this is still an area that we're doing work on. Yes. So the question was, if you want to use your own analyzer with GoPlease, do you have to rebuild GoPlease from source? Yes, for now. Though we're working on ways of like integrating your analyses into GoPlease without rebuilding GoPlease. Yes. Oh, yeah. That's an interesting idea to write an analyzer that checks your code and then suggests analyzers that you can run on your code. Yeah, very meta. Love it. Any more questions? Okay, I think that's it. Thank you.